Hello, welcome to the third part of the chapter on kinetics. So to talk about this, I'm going to talk about how temperature affects chemical reactions, and I'm going up. What I'm building up to is what's called the Arrhenius equation. So the idea is, the more collisions there are, the faster chemical reaction will go. So let's say, for instance, I'm looking for a date. Okay, and I'm looking for a date. How is it more likely that I'm going to find someone to partner with me to go to the American Chemical Society ball? Okay, I need a date for the American Chemical Society ball, and where do I go? So I can go to a place. Maybe I'll go to the beach. So if I go to the beach that has lots of potential partners or a sparsely populated beach, which one I'm more likely? I'm more likely to go to a place that has lots of potential partners. Why? Because if I'm going around talking to people, I talk to more people. So there's more of a chance that someone will like me. And also, let's say the way I'm doing this, I go up to someone like, hey, would you like to go to the American Chemical Society ball with me? And if that person says no, then I will walk to the next person and say, hello, beg your pardon, could you find in your heart to accompany me to the American Chemical Society ball? And how can I improve my chances? Instead of walking, what if I ran? If I ran between asking someone, I can cover more ground. That way I can ask more people. More likely I'll find a partner, right? Of course, it doesn't work the same way, huh? With people, it doesn't work the same way. The idea is with concentration, temperature, there's more collisions. So higher concentration means more collisions, and so it's just banging together. In order for two atoms or molecules to react, they have to physically touch one another. How do they physically touch one another or get close enough that their electron clouds will interact? More concentration means more collision. There's more interaction. Higher temperature means it's moving faster. It's moving faster, so there's more collisions. And then the third thing that affects chemical reactions is catalysts. So catalysts, they can do a couple things. They lower the activation energy. We'll talk about that soon. And or they can cause more effective collisions. So let's say I'm trying to form this molecule from these two reactants. So more collisions, so they can collide like this. This tends not to make a chemical reaction. This probably won't do, but this collision can form this molecule. So you have to have the right type of collision too. So orientation is important. But what really happens, so when two things are moving around in space, two molecules, is when they approach each other, they slow down. Why do they slow down? Because there's a negative electron cloud here. So the kinetic energy is turned to potential energy. So two things, they approach, and there's not enough energy, then they fly apart. But if there's enough energy, they can approach and they can collide, and then they might react. And this is something we're still researching, but you can have a collision come on like this. So things are moving around, they collide like this. Then these molecules can dance around, and they can form transition states, and then they might react. So if there's something that reacts 1 out of every 10,000 collisions, that's considered a very fast chemical reaction. This is something we're still studying, and it's something we don't entirely understand. So that's how the collisions work. And then the catalysts, so a very common set of catalysts we use biologically are called enzymes. And enzymes are just big blobs of protein. And they hold something, they take something, they hold it, and they take something else, and it can be two enzymes, it can be one. They hold something, they hold it in the right way, and then a chemical reaction happens. One collision, perfect collision, happens once, and it breaks away. So it'd be like, let's say I wanted to beat somebody up, and have you ever seen people fight before? It's entertaining. I mean, because usually nothing happens, right? Like you're talking to me, yeah, I'm talking to you, yeah, and people just kind of dance around each other for a while, and they're like, you know what, you're not worth it, and then their friends pull them away, right? So that's how kind of fights tend to be. I mean, maybe someone will throw a punch, but it's usually nothing happens. It's comical, really. I mean, unfortunately, it's kind of comical. Let's say you really want to hurt somebody, say like, all right, I want to beat that person up. So what I'll do is, all right, I'll tell my friends, you know what, go jump that guy and put that person in a full Nelson. And with that person in a full Nelson, I can come up to that person, take a look at him, and one punch, knock the person out. That's what an enzyme does. An enzyme does, and it grabs somebody and holds a molecule in just the right way, and then this the right way that can react with something in just out in the air, something like oxygen. Or you can have an enzyme, another enzyme comes, they come together and they react and then they break off. So we'll talk more about that later, but that's how catalysts work. Okay, but let's focus more on these collisions. And we mentioned rate constant is K. So rate constant, what rate constant really is, it's a function of temperature. And this is the Arrhenius equation. Rate constant is equal to some species A raised times e to the minus EA over RT. A is known as a frequency factor. This is the number of effective collisions. So remember, not every collision is going to happen. It has to have the right orientation. Sometimes we describe A as a function of the orientation times the number of effective collisions. That's partially true because we've also found out that molecules like to dance. So this is something that we're still figuring out. We can see this experimentally, but the variables, this is known as a lump sum approximation, and we've semi-empirical model based off of this. So sort of empirical model. I talked about this before. This is a semi-empirical model. So we're throwing a lot of variables into that A term and just saying it works over a certain period of time. And the EA, this is the activation energy. And the activation energy, so I'm showing this chart here. The y-axis is energy, specifically potential energy, and the x-axis is the reaction progress. Usually it's reaction progress is usually internuclear distance. So what happens, like I said, you have two high energy atoms, molecules going around, and they approach each other. What happens? They slow down, and then their activation, their potential energy increases because of the electron repulsion, and then they can reach, we call this part right here, that's called a transition state. So it's kind of like if you're dating someone and then you get married to someone, there's a transition state there. It's the engagement period, right? So there's single and dating, and then engagement, and then married, kind of thing. And so you could argue that dating in itself is a transition state. So you can have more than one transition state. So so molecules can come together, they can dance, they can form something else, and then they can rearrange to another transition state, and then they can make another reaction. So it's really depends on the chemical reaction, depends on how the reaction progress goes. This transition state is oftentimes a saddle point on a potential energy surface. So it's not always that way. But and also notice here the way that this reaction is written, it's exothermic. The energy of the products is lower than the energy of the reactants, and then so there'll be energy going off. Okay, so thermal energy distribution. So the y-axis here is a fraction of molecules, and the x-axis is energy. And so the far right one, the red line, has higher temperature. The middle one is lower temperature, and I've drawn in violet super cold. So and there's a small fraction in the super cold, a small fraction of activation energy, and at various temperatures. You can see that there's just at higher temperatures, there's more reactants that have high enough energy to react. So and I'm putting the super cold in there. So have you ever seen really, really old paper? We're talking like 1,000 years old, something like a Gutenberg Bible. If you ever see paper that's really, really old, it looks like it's burning. It looks like it's slightly burnt. And the reason is because it is actually burning very, very slowly. And because of that, at this temperature and pressure, there's a really tiny amount of oxygen that has enough energy to react with the sugars or whatever. I'm assuming it's made of maybe, or it could be vellum, I guess, with the sugars or proteins in the cellulose or the vellum paper, or the reeds, like a Dead Sea Scrolls, or maybe it's made of reed or something like that. It's more cellulose, so sugar. And so it can take thousands of years to burn paper at a standard temperature. Or you can take a match and light paper on fire, and it'll go away in a matter of seconds. So so it turns out this is it's called a rule of thumb, a general rule that every 10 degrees Celsius the reaction rate tends to double. So if you're looking at 25 degrees Celsius and a flame, depends on the flame, 600 something degrees Celsius. So you can see how many times it doubles. That's the reason why paper burn. It's one of the reasons why paper burns so quickly under a candle flame versus this temperature, right? So much faster versus hundreds of thousands of years. So not in the textbook, but there's actually you can have too much energy. So activation energy works as a range. So if you're forming this molecule from these, there has to be enough energy for it to overcome the electrostatic repulsion. But let's say you have two molecules that are going too fast. If they're going too fast, they just bounce off of each other. So this is more of a exotic case, but there are some cases where increasing temperature actually slows the chemical reaction. That's not typical for most things, and that's usually only see that in astrochemistry. So it's like, why don't we get chemical reactions that happen on stars? Why aren't we forming organic molecules in stars or under conditions that are really hot, like circling a black hole? Why don't we see molecules there? It's because it's going too fast, and they don't stick together. They're going too fast, and the chemical reaction doesn't happen. So that's not on the test. That's just, I like to talk a little bit above and beyond the course sometimes. So okay, this is the Arrhenius equation. K equals frequency factor A times e to the minus EA over RT. K is the rate constant. Let's take the natural log of both sides. Natural log of K equals e to the minus. So natural log gets rid of the exponent, and then we have the plus ln A there. So let's write two of these, so K2 and K1, and let's subtract them. If you subtract them, the natural log A goes away, and we can solve that for ln of rate constant of the second over the rate constant of the first is equal to the activation energy over R, 1 over T1 minus 1 over T2. So if you haven't noticed, you've seen something like this before, the Clausius-Clapeyron equation. So you're going to see lots and lots of natural logs throughout this course. So that's why I told you, if you're having a hard time with natural logs and you thought, oh, I'll never use this again, guess what? You're going to use it now, and we're going to use this in the future. So if you're having a hard time with this, please come see me. So let's look at the Arrhenius equation here. The rate constant for this reaction at 701 Kelvin is equal to 2.57 inverse molar inverse seconds, and at 895 Kelvin, it is 567 inverse molar inverse seconds. So, and what does it want? It wants the activation energy. So, I like to do, so I've written the equation here. I like to do all the math first. So, what I can do, I can multiply both sides by R. So I can look at this one, ln, I'll write it out, ln K2 over K1 equals EA over R, 1 over T1 minus 1 over T2. And we can divide both sides by 1 over T1 minus 1 over T2. And I'm going to delete this. So, and I'll just move the R over here, multiply both sides by R. And this is what the activation energy is. Just like that. I'll move the equal sign down too. Oop. Let me move the equal sign there. I'll move the activation energy sign there. So just put in the numbers. Okay, 8.314 times the natural log K2 is 567, and K1 is 2.57. I know the inverse molar inverse seconds, they will cancel. 8.314 joules per mole Kelvin. And then we have 1 over T1, 1 over 701 Kelvin minus 1 over 895 Kelvin, and the kelvins cancel. So because 1 over Kelvin, this equals Kelvin, and joules per mole Kelvin, the kelvins cancel, the Kelvin times the 1 over Kelvin cancels, or you could argue that the inverse kelvins cancel. So however you want to look at the units. So our units are going to be joules per mole from R there. And let's look at this number, and let's look at what we expect. 1 over 701 minus 1 over 895, that's going to be a small positive number. So remember, 1/2 minus 1/9, that's a positive number, right? So the bigger the number on the bottom, the smaller the number actually is. So that the denominator is a small number. So and then we have the natural log of 600 over 2.5, 3-ish. That's going to be a decently sized number. So that is going to be the natural log of 300-ish, and that's going to be about let's see here. So natural log of 300. That's going to 20. So natural log of 100 is not log of 100 is 2. So that's going to be close to 100-ish because it's 2.3 times the log of that. So anyways, I'll start in the calculator. I expect that number to be about 100, the natural log of 567 over 2.5. So I expect that to be about 100 times 8. So that's about 1,000. And then divided by that, I have no idea what that's going to be. It's going to be a big number. Comes down to it. Okay, well, let me just put it in the calculator. Okay, so putting these numbers in the calculator, we get 145,096 joules per mole, and it's asking for kilojoules per mole, the energy, activation energy in kilojoules per mole, and then so 3 sig figs, so 145 kilojoules per mole. So why don't you try it for this one? So go ahead and pause the video and I will set it up for you to check the answer. So if I put in these numbers in your calculator, you should get an answer close to that. I got a little bit off. I guess the float on this calculator, you can get something called truncation error. So either way, plugging in the values, this is what you should get. Okay, moving on to reaction mechanisms. So reaction mechanisms, it's the overall reaction, not just the step. And the slow step is what determines the kinetics for the reaction. So I don't know if I mentioned this before, but I'm a 4th generation chemist. So my parents are both chemists, and my mother is a chemist, her mother was a chemist, and then my grandmother's father is a chemist. So I was raised with a lot of chemical knowledge and just things. So I remember if I was taking too long getting ready for the family to leave, and my mother would tell me, like, Mike, you're being the rate determining step. So we can't leave until you're done. So I kind of understood, oh, growing up, oh, I'm the one slowing everyone down, so the family can't leave until I'm done. And so when I learned about chemical reactions, I was like, okay, well, that makes sense. You know, that the slow step is what's going to rate limit it. And here there's a picture of a traffic jam caused by a holdup there. I also think about Thanksgiving and turkey, cooking a turkey. It's the rate determining step for Thanksgiving dinner is a turkey. Okay, so that's really what decides when you're eating dinner, is how long it takes to cook the turkey. And that's just for one. So imagine that you're making Thanksgiving dinner for 50,000 people. So what's and if you're in charge of Thanksgiving dinner for 50,000 people, what are you going to pay attention to? You're going to pay attention to turkey cook time. Then you're going to have to manage the amount of time to cook that turkey, whatever it is. If you're baking in the oven, or whatnot. I'm thinking about baking in the oven. That's really slow. It's faster if you put it in the deep fat fryer, of course. But so, anyways, but that's the turkey is kind of what changed when you really have to focus on in that. Okay, so rate mechanism. So the overall reaction, not just a step. Rate determining step will assign the kinetics for the reaction, and the rules are the steps in the reaction mechanism must sum up to the overall reaction, and the rate law predicted must be consistent with experiment. So if you look at this, what it probably tells you, this looks really simple and basic, and it's because we made it up. And it's because this is how we know to do it. We're a little bit better, but this hasn't changed since the 1960s. So when Linus Pauling wrote the book on freshman chemistry, not a whole lot of chemistry has changed. So you're looking at chemistry at the height of our knowledge in 1960s. We've learned a bit more since then, but I mean, and we're better with kinetics because we have more spectroscopy. So we can look at things, we can actually probe things in their transition states. So we know that transition states are real and they exist. But a lot of this here, we're just guessing, and a lot of things we're still guessing. We know it works, and we think this is what happens. So, okay, let me talk a little bit more about this. We have the reaction progress, and we have these two transition states, and then we have the product. So we have to, when we determine this, it has to be consistent with the experiment, like I said, and we can label this as a possible reaction mechanism. And the other thing about reaction mechanisms, there's multiple of them. They don't just happen. And when you have a chemical reaction, there's more than just one set of products. So a famous one is flame chemistry. Flame chemistry is not well understood at all. We are trying, and lots of people are interested in flame chemistry. The Air Force spends lots of money on this because, I heard of a heat-seeking missile. They're actually looking at the soot coming from the back of a jet. So it's the heat-seeking missiles are actually a radar signature. It's not seeking heat. It's seeking a radar signature from soot. So the Air Force is always looking into ways to make things more stealthy, for instance. And the more we know about flames, we use flames for many things. We use it to heat things up. We use it to cook things. Of course, more for heat things up. Most of our hydrocarbons are flames, internal combustion engines for gasoline and diesel. So lots of stuff we don't know, and we know we can make it work. A car will still drive, but doesn't mean we understand everything. Okay. So here is in the textbook we experimentally determined the rate law of this equation. So we have 2 hydrogens plus 2 nitrogen monoxides makes 2 waters and nitrogen. And the reaction rate law is K times concentration of hydrogen for first power, nitrogen monoxide of the second power. So we're proposing a reaction mechanism here. Is this valid? And what the book doesn't explain it very well. Let me explain this a little more detail. To do this, they don't mention this. You apply with something called the steady state approximation. The steady state approximation means that the concentration of intermediates is constant. And the intermediates here are N2O2 and N2O. Okay, so, and the kinetics are decided by the slow rate determining step. So we write out the slow rate determining step. That's the middle one, and it's going to be the rate is then going to be the K2 listed in the chart times the concentration of hydrogen times the concentration of N2O2. I'm getting this from right here, if you're not following. So I'm getting that from there. So I'm writing that. But what the heck is the concentration of N2O2? It's an intermediate. And what I've written there, that's called elementary. You're just writing out the reactants rates or stoichiometric ratios. So if this is constant, so I'm sorry, if this concentration is constant, the N2O2, that means that the forward and reverse reaction have to be the same. So this here is the forward reaction, this here is the reverse reaction, and then we solve for the concentration of N2O2. And we plug this back in. So we take this and we plug it into here. And then the rate law, well, I should say we take this and plug it into there. And then we get the rate law equals this. And I know the book doesn't really go over it that much in great detail because it doesn't talk about the steady state approximation, and that's assuming the intermediates are constant. What do you do if the intermediates are not constant? Then you have to do more differential equations for it. But the intermediates I've highlighted, those are the intermediates, and they are generated and consumed in the reaction. This book was written in the 1960s kind of style with contemporary tools. We can use spectroscopy to figure out that if there's these things present. We can use spectroscopy, we can further verify this. But we might find other things. So the thing is that we might find other things, and there's more than one reaction going on. There can be more than one way to reach the products. So this is a very advanced topic. What does that mean for you as a student? It's going to be real basic ones. So actually, this one is written here is too hard. This is way too hard. I'll go over, if you look at some of my test reviews and in the homework, there'll be much easier ones than those. So let's talk about catalysts. Catalysts provide an alternative path. They're not consumed in a reaction. Homogeneous are the same phase. Heterogeneous are different phase ones. The heterogeneous catalysis, these are the more powerful ones. So how do they work? Well, let's see here. We have, so if you look at this graph here on the right, potential energy is the y-axis, and the reaction progress, reaction coordinate is the x-axis. You can have a catalyst that puts easier transition states going forward. So what does that mean? And now, mind you, if you live on Oahu, or if you live on Oahu, that might help. Say that you want to go from the airport. I'll use a different color. Say you want to go to the airport and you want to go to the Marine base there in Kaneohe Bay. In the olden days, you would have to take this route here. So that's if you can't see that, you read. So going here, is that easier to see? Yeah, around the island there. So, but if you live in Oahu, you know that there is an alternate path. You can take H3 and get there in a straight shot. So just like H3 can catalyze your trip from Pearl Harbor to the Marine Corps base versus going around the long way past Tanama Bay, a catalyst in a chemical reaction provides an alternate path that's lower energy and will get you there faster. So written in the book, the homogeneous phase, so this is ozone depletion. Ozone plus oxygen radical makes 3 diatomic oxygens. And if there's a chlorine radical, this can react with ozone to form ClO plus O2. The ClO can react with oxygen radical to form oxygen and chlorine. And then if you look at this, the ClO goes away, and actually this is going to be 2O2. There's a mistake here. 2O2. So those overall reactions sum up, and then you have these intermediates. The ClO is the intermediate, and the Cl catalyst that is consumed, that is regenerated back in the reaction. So even though it changes form, it reappears. So it is a proper catalyst, and it's not consumed in the reaction. Therefore, this will make the reaction go faster. That's not real. That could happen. The real danger with ozone depletion is that it can be a heterogeneous catalysis as well. So volcanic ash and or ice crystals, and also halogens can absorb on these, and you can get the chemical reaction happen on the surface of those. So actually it proceeds much faster than the homogeneous phase. So homogeneous phase tends to be slower than heterogeneous phases. Also, a lot of metals, so like transition metals, are homogeneous phase catalysis, you can get things absorbing on the two different structures in the metals. The metals can form tetrahedral and octahedral structures, and then the chemistry can occur while the species is attached to the metal, and that was considered homogeneous. Let me show you some pictures of heterogeneous catalysis. So platinum is a very useful catalyst. Platinum is actually more common than gold, but platinum costs more than gold because platinum is very useful. So you can put hydrogen and alkane, so it's carbon double bond, so ethene or ethylene with hydrogen. It can react on the surface, and then it can pop off. There's a whole branch of chemistry in this. There's something called physisorption, where it's just physically on the surface, and there's chemisorption, where it will chemically react with the surface, and you can chemisorb and then react that way, or physisorb. There's a whole bunch of stuff that goes on here, but you can you can use platinum to react, and platinum is very reactive, and we use it in our catalytic converters. Our catalytic converters in the car, and this catalytic converter was started using in the 1970s. Air pollution, actually the Earth is much cleaner after the passage of the Clean Air Act. We've greatly decreased many of our pollutant levels because of that. And so if you look at these here, the pollutant levels have gone way down. And it's a part of it, well, it's the Clean Air Act, also transportation with the advent of the catalytic converter. Platinum is very expensive. How do we do that? We found this out accidentally in the 70s, that if you take a little bit of platinum and you put it on a zeolite is like a clay. It's a very honeycomb, open channeled clay, that you get a catalytic converter that works. It turned out it was nanotechnology. And I'm showing this picture here below on the left, that we have these nanoparticles of platinum, and then the chemical reaction is happening on the surface of these nanoparticles. And that way you don't need to have a big sheet of platinum. You can do it with a little tiny bit of platinum and go much, much further. And so we didn't know that at the time, but that's nanotechnology. And there are other cases of accidental nanotechnology. So the pink and purple colors in the rose windows of European cathedrals actually turned out to be gold nanoparticles. So the artisans, and this was lost technology, the glasses were stained, and then we lost the knowledge of how it worked. It was a mystery. We had no idea where these colors came from. But then when we started studying gold nanoparticles, we noticed, like, hey, these colors are just like the colors in the rose windows of the cathedral. So we looked at them a little more closely, like, yep. So in the Middle Ages, artisans figured out how to make gold nanoparticles and put them in glass. So they did it by trial and error. They didn't do it with spectroscopy or anything. It was just they tried some stuff over and tried different things, and they found out if they did these conditions, we got this color. If we changed the conditions, we got another color. So very pretty. I love those churches, especially the Gothic cathedrals. I always like that, like in Notre Dame and whatnot. So I'm a big art fan. Okay, so, and I mentioned biocatalysts. Enzymes are biological catalysts, and how these work is enzyme plus substrate, so S is substrate. Enzyme plus substrate turns into an enzyme substrate, and then the enzyme substrate can regenerate the enzyme plus the product as a slow step. So, for instance, you can take sucrose. So sucrose is a disaccharide. It can break apart into glucose and fructose, and we can do this by making the enzyme, and we have the enzyme is like this big blocky thing. It's a big blob of protein, and then we have the substrate comes in there, and then a chemical reaction can happen. So, and shape is very, very important with enzymes. So I'll explain that in a second, but So I remember when I was a kid, uh, I used to like to take cotton candy. I like cotton candy. Well, I haven't eaten in a while, but I guess I would still like it now. But cotton candy, I've noticed if you lick it. So if you take cotton candy and you lick it and just let it sit there, it will digest. You can watch your saliva digest the cotton candy just by licking it. And I used to think that was really cool when I was a kid. And there's an enzyme in our saliva called amylase, and amylase will digest simple sugars. So you can digest candy in your mouth. And you, like the old commercials, if you've seen how many licks does it take to get to the center of a Tootsie Roll pop. You can digest lollipops or suckers, or whatever you want to call them, or Jolly Ranchers. You can digest those in your mouth, but you can't digest things like meat. So you can't if you put a piece of steak in your mouth and you let it sit there for a while, you're not going to digest it. It's just maybe if you chew it, you can mechanically break it apart. But your saliva alone cannot digest meat, but it can digest simple sugars like candy, like sucrose and stuff, and candy. So, uh, so if you ever wondered about that, like why if you lick cotton candy it starts to digest outside the body because of the enzymes, and the enzymes are biological catalysts. Other thing is so temperature. So, well, the shape. Shape is very important. You can change the shape of catalysts two ways. Well, it's catalyst enzymes two ways. One is the pH. The other one is the temperature. So we tend to cook our foods, right? We cook our foods because it makes them safer. So it makes them safer that way, and so because it reduces the risk of infection. So and if you notice something like if your hands and like in motion, there's lots and lots of catalysts going on. A lot of enzymes are at action just moving my hand. There's catalysts involved sending the nerve signals through. There's catalysts involved in moving my muscles and that kind of thing. And if you damage your hand with high heat, like a third degree burn across your hand, can you move your hand if it's third degree burns? The answer is no, you can't. Why? Because the heat has destroyed all your enzymes and they no longer function. Therefore, the proteins just don't work and you can't do those things. So the temperature will destroy the function of the proteins. And another thing that can destroy that, as I mentioned, was pH. So you can cook food with juices. So you can use lime juice. Lime juice is pretty acidic. You can cook fish with lime juices, and that's fine. It works. Our stomachs can do that too. We have very acidic stomachs. So we have our so we I don't recommend you eat raw meat. I eat raw fish, so I guess I have eaten beef tartare. So I guess I have had raw beef before. But I mean, it's a risk. It's a risk when you eat undercooked food because it increases your risk of infection. And it's easy to make it safe. Heat it up to 165 Fahrenheit. That kills most bacteria because of that. So that's something by shape is important. And also for the pH, we have our lungs and our kidneys. Those regulate the pH in our body. And we'll talk a bit more later. But if you have a patient who has issues with his or her lungs and or kidneys, that can be a bad thing because if you're it can cause the blood pH to go up and down. If the blood's pH goes up and down, that can result in organ failure. If organ failure happens, systems start going down. When systems start going down, patients die. So and that is all tied to the function of enzymes. So, okay, well, it's a kind of a morbid thought to end it, but what we haven't talked about here, though, is control. The important thing for all these is control. How do we control chemical reactions? And now we've learned a few ways now that we've learned why chemical reactions happen. In future classes, you can learn how this is controlled. And there's lots and lots of business involved in this. How to control chemical reactions, how to speed them up, how to slow them down. Sometimes we want to slow them down. Sometimes we want to speed them up. Why do we want to slow them down? Because if there is a product that is harmful or costs a lot to dispose of. You don't want that chemical reaction to happen, or maybe you only want it to happen halfway. Lots of possibilities. So I will end there, and I will see you for the next chapter.